My name is Professor Simpson. I work at the University of Toronto in Canada, and I'm a co-founder and director of the Environmental NMR Centre. I actually worked at NMR for 30 years now, and I started actually looking at the structure of soil, looking at extracts from soil, and everyone told me that NMR just wouldn't work for soil. But no one could tell me why it wouldn't work for soil. So one day I just stuck in some organic extracts into the chemistry queue, and the data I got back was amazing, and from that point onwards I was completely hooked on NMR. My PhD basically became a PhD on NMR spectroscopy. I'm working on the development of environmental applications of NMR. So one of my areas is to look at in vivo organisms and how they react to the environment, to understand why they're stressed and why contaminants are toxic. Another program looks at discovering new contaminants and what around, in the world around is actually problematic to humans and the environment itself. My final area is sort of hardware development. So we're trying to make NMR more accessible, especially towards low field instruments and even maybe in the future portable instruments. I like to say NMR is the ultimate sort of discovery tool because it's the only technique that can really map out structures from scratch without the use of prior information. So it's really important for environmental because if we always search for things we know that are there in libraries, we kind of get a bias towards looking for just those things. So unexpected things such as new contaminants can be missed potentially for decades. So that's probably best explained with a couple of examples. So the first one that's kind of interesting is you've probably all heard of forever chemicals, these perfluorinated chemicals in the environment. They're actually quite bad for humans because when you get them in your bloodstream, they can actually they have a half-life of 200 years because they bind irreversibly to our proteins. And we always think of detecting using mass spectrometry, but interestingly, in 1976, a medical doctor called Donald Taves actually put his own blood inside NMR and found all these fluorinated peaks and published a very small paragraph on it. And because we don't use NMR in environmental research, it was undiscovered for 2 more decades. And so it's a really good example why we should use NMR more in environmental research. And the second example is actually from the Environmental NMR Centre itself. And the University of Washington, the EPA reached out to us back in about 2019, now at the start of COVID. And they had this sample they thought contained a toxin. In fact, what they've been seeing is that the salmon across the whole west coast of the US and Canada were dying when they went back and swam upstream. And nobody knew why. Some people said global warming. Other people were saying there's some toxin. And we had this sample, and they asked us, is there anything you can find in this sample? And as luck would have it, it was the start of COVID, so they shut my lab down for 6 months, and this sample was actually stuck inside. So I had remote access from home, and I went a bit crazy on it, and we dug through and dug through. We ended up finding this new chemical called 6-ppd quinone. Now, 6-ppd, the parent molecule, is actually added to tires to stop them cracking. And it turns out that when the tires rub on the road, they leave a small thin layer, and that reacts with ozone to form 6-ppd quinone. And this is so toxic, there's enough chemical in one tire to kill 50 billion salmon. And it's turned out that it's actually got influences on human health. They've connected to many respiratory diseases already, and some people think it's connected to Alzheimer's disease. And they're doing a global ban of this now. So it's a great example, really, of how NMR can be used as a discovery tool and how important it is to use it. And we have to use it as a complementary tool alongside mass spectrometry environmental research. And so I'm very excited about the Fourier 80 because it makes the NMR technology more accessible to the community. I think low field's really exciting because it's accessible. It's even a little bit easier to use than high field NMR. And it allows new users to come into the community that maybe can't have access or opportunities to use high field instruments, but can get access at low field and then kind of get excited to see the potential of NMR and then eventually probably move to high field as well. I think the key goal was to show that benchtop NMR could be a really powerful technique. So it's easy to say, okay, maybe benchtop doesn't have the sensitivity or the resolution of a high field instrument, but if you apply the latest cutting-edge experiments, we can get rid of the overlap and we can actually increase sensitivity, sometimes as high as some high field instruments. What I really, really love about the Fourier 80 is you can actually port experiments directly from the high field systems to the 80 and run them directly. So that means you have thousands of pulse sequences at your fingertips straight away. And I see that as really important because environmental research is very diverse and it has many different nuclei and many different experiments. And so I think it's a great tool to bring. And I wanted to show in this paper that we can do it. It doesn't have to be that difficult. Well, at the fundamental level, NMR allows you to map out the structure of a molecule, nuclei by nuclei, to solve a structure from scratch. In fact, it's the only instrument that can do that arguably with the exception of crystallography, but you can only crystallize about 5% of structures, making NMR really powerful to understand the structure of something you don't know. But also, it can be really important for composition. So maybe you're studying soils and you want to see how climate change has impacted them, or you can study the carbon distribution in those soils and what's happened and the mechanisms behind that. And finally, it's the most versatile technique I can think of. For example, you can do solids, you can do gels, you can do liquids, you can do gases, any combination of that. And I can't think of another instrument in modern science that can actually be that versatile. I'd love to see one day that environmental NMR and maybe Benchtop NMR to start with could be used in agencies such as like the EPA and Environment Canada. For example, we have projects at present where we're screening industrial effluents across Canada and actually being discharged directly into the environment, and we're seeing all sorts of classes of molecules we didn't expect to see that aren't currently being monitored or thought of as traditional contaminants. With the EPA, they're sending us carpets and cosmetics, and they're asking us to understand the flooring components. And some of these species have polymers in that are very difficult to analyze when they're bound to the carpet using current methods. But in NMR, we can see them like within 1 minute. So Benchtop NMR does have the sensitivity and capabilities to address these problems. What we have to do, I think, is produce some easy-to-use protocols so that this makes it accessible for new users in the field.